text. I'm not sure if I can remember everything, but yeah, no worries. Okay. Hey. So shall we start? Yeah. Okay. Okay. So hello everyone. Um, Glad to see you here. It's my great pleasure uh, to be here again and to give you this talk, share with you some of my experience on, robot perception and learning stuff. So my name is Zhi Yan, and I'm currently an assistant professor at the University of Technology um, of Belfort-Montbéliard in France, and I'm assistant professor of computer science, and also no, uh, referent for open science there. So the university is located in the east of France, very close to Basel and Freiburg. Um, so my current research interests include especially mobile robotics, including autonomous driving and chronorobotics. Um, so I was previously postdoc in the Lincoln Center for Autonomous Systems, L-CAS, at the University of Lincoln in the UK. I was mainly working on this H1010 project, FLOBOT for flow washing robots for professional users, and many involved in two tasks. One is human um, one is human tracking for safety, and the other is environmental reasoning and learning. Um, I was also involved in another H1010 project, ENRICHME, for enabling robots and assisted living environments for independent care and health monitoring of the elderly. I was working mainly on this thermal-based no, this logic monitoring. Before that, I was postdoc in the cartoon at the IMT Nord Europe, which is the new name. Previous name was Mindway Research Center. I think probably is more popular with this name in France, and was working on this regional project on this software engineering for robotics, especially for mobile robotics. So I got my Ph.D. in computer science from the University of Paris VIII. So motivated especially by this Robot Cup soccer. So the idea to mention this Robot Cup is just that this year Robot Cup will be held in France at Bordeaux. So if you have time, and welcome to France and join this fantastic event. So I'm going to talk about this robot perception. Perception in general, according to this great book, psychology is the organization, identification, and interpretation of sensory information in order to represent and understand the presented information of environments. So this is like a perception in general. So basically, if we take ourselves as an example, it's quite easy to understand this, this idea. Intuitively speaking, robot perception is just to use various sensors and algorithms to simulate these capabilities. For example, see, hear, test, and so on. So probably the first capability, which is sight, is one of the most popular topic in our community, mobile robotics, which includes especially two kinds of sensors. One is visual, the other is non-visual. The former include monocular stereo RGBD fisheye cameras, and then also many other kinds of cameras, while the later include LiDAR, radar, sonar, etc., etc. Another fantastic perception type is actually this chronoroception. Sometimes we call it time perception, which is a little bit beyond the scope of today's talk. But if you have any questions, we have some experts here at the CTU, especially guys from this fantastic lab, chronorobotics lab. So previously, I actually made a perception system for our autonomous vehicle at UTBM. So I installed up to 11 different sensors onto autonomous vehicle. So here are some representative non-visual sensors, such as 2D LiDAR, which is widely used in the SLAM community. 2.5D LiDAR here for with only 4 layers, scan layers. And we have two 3D LiDARs here. So each one with 32 layers, scan layers. Then we have some visual sensors here, like a fisheye camera, stereo camera here too. So just to give you an overview idea about these two kinds of sensors for simulating the sight capability, the sight sense. And here we could have an intuitive idea about the field of view, or say the visual scope of different sensors. Some projects and also examples in which we used different 3D LiDARs for no vision sensors. So here are the robots you probably know even better than I at the CTU for the DARPA challenge. So here is actually a 3D LiDAR installed on the Jaka robots. So this is the robots we developed for the FLOBOT project. One of these man perception sensor is the 3D LiDAR on top of it, which is a Velodyne 3D LiDAR with 16 layers. Here is another robot used for one of my colleagues' project. Also, one of the main perception sensor is a 3D LiDAR. This is the car autonomous car I just mentioned here. Okay, two Velodyne here, 3D LiDARs here, and 2 LiDARs in front of the vehicle. So I think in order to better understand the concept of the LiDAR or no other no visual sensors. Here is a figure to explain this idea. So typically we have a fire sender just to fire a laser beam. And when this laser beam reached an obstacle, for example, the wall over there, this laser beam should return then back to the sensor. Thanks to the a receiver inside of this integrated of this LiDAR, so actually the device can get the echo of this laser beam. So since we know when we fired the laser beam and when we received the laser beam, and we know the time of flight, right, which is a constant here. So easily we could calculate the distance between the device and the obstacle, divided by 2, because this is like a go and return journey, right? So essentially, a LiDAR, sonar, radar, they are always the same principle, which is a time of flight. And essentially, these no visual sensors are for distance measurements. So in another word, if you played with different cameras, you know that the data we actually get with these no visual sensors are a little bit difficult to interpret because they are essentially no distance for distance measurements, while cameras are typically for this context understanding with rich color, texture information, something like that. So with different purposes. That's why at a very early stage, 2D LiDAR is really widely used, especially for this SLAM problem, SLAM for simultaneous localization and mapping, one of the fundamental problems in mobile robotics. So 2D LiDAR was widely used for this purpose. But at the same time, some researchers were also interested in this question: how to use this kind of sensor to understand, to better move the environment. For example, for obstacle detection, for object detection, including humans. However, as you just saw here in this video, the capability of this 2D LiDAR is quite limited for object detection such as human legs, right? Because the information is quite limited, only a few points, and for forming a plan, right? So that's why people started to investigate this 3D LiDAR. So 2D LiDAR gives you XY information, but with 3D LiDAR you can get XYZ information, which allows us to even better understand the environment. So 3D LiDAR is becoming more and more popular, including but not limited to mobile robots, autonomous driving, environmental monitoring, and so on. One of the things I would like to mention here before really touching our topic is the last application, environmental monitoring, because using 2D, 3D LiDAR can give you, these two very important benefits, long-term operation and privacy. Because with 3D LiDAR, we can monitor 24 hours per 24, which means over the night, not really affected by the lighting conditions. And also, since with the spirals and the points generated by 3D LiDAR, we cannot really identify the person. At the earliest, actually a Velodyne's 16-layer 3D LiDAR contribute to the success of Stanford's Junior Robot Car, which is actually the Sebastian and Turns team in the DARPA challenge in 2007. Because the main sensor used by this autonomous car for obstacle detection, such as pedestrians, traffic signs, and other cars, is just the 3D LiDAR, the Velodyne LiDAR, 3D LiDAR with 16 full layers. So this 3D LiDAR actually contributed to the success of Stanford's car, which actually made them the single one, the only team to be able to finish the whole race. And but at the same time, this success, this championship also contribute to the popularization of the 3D LiDAR, because the community started to pay attention on this kind of new, at that time at least, new device. Say, wow, compared to 2D LiDAR, 3D LiDAR can really something beyond just mapping of the environment, right? Can really give you more information about the environment. So if you search for the keywords 3D LiDAR robots on this Web of Science, we could find out that the number of paper publications really get increased over year since 2018, right? Just the year after the DARPA challenge. And if we check the industry, or let's say the commercial side, we could see that many industry players entered to this market. For example, Velodyne started in 2005, then Carnegie valued at over $1 billion in 2016, right? So these results actually retrieved from a report in 2019, so it's not up to date. But I couldn't find any other report similar to this. So the 3D LiDAR is getting widely used in many domains. One of these is a service robot. So here are two videos to show this application. So one is from the European project, FLOBOT, for human detection and tracking by using 3D LiDAR on top of it here. And the other is from another European project, Iliad, for this industry for kit. And also one of these sensor for human detection is just a 3D LiDAR. Another application is I think the very hot topic of today, which is autonomous driving. The video here shows some results from an industry player, which is called RoboSense. It's a Chinese company which is specialized on this 3D LiDAR, building making. So this is an example of using 3D LiDAR for highway driving. As you can see, many other cars are detected by this 3D LiDAR, and also their velocity are estimated by the 3D LiDAR. Not only with, of course, some algorithms, for example, for object tracking, something like that. You might know that if we use radar, right, which is another visual sensor, we could actually get this information, this velocity, directly because of thanks to this Doppler effect, right? I also learned this morning. Doppler was here, right? Many years ago. Yeah. So this is another video to show one of the purposes of using 3D LiDAR for building a map, and not a 2D map, but a 3D map of the environment, right? So this map can be can be also used for autonomous driving, but the question we usually have here, the problem we usually have here, is too costly to use this point cloud map, or too heavy, or we could say the file is too large more directly. Probably you heard about this modern mapping or localization for autonomous driving. Could be this HD map, high definition map based, or even mapless navigation without map, right? So let's give more information about on the data representation and processing of this 3D LiDAR. So essentially, the data, sensory data generated by 3D LiDAR is just a set of points, a set of 3D points, which can be represented as like doesn't work. By this equation. So the data processing methods are really data processing methods really depend on the problem. Say different problems might need different data processing methods. For example, for mapping and localization, we have typically two categories. Either we process treat this data at the point level or at the feature level. So point level, some famous algorithms like iterative closed point ICP, normal distribution transformation, NDT. So which means we really process point by point. And if we want to have a little bit, let's say, higher level data processing, then we could consider this feature-wise methods. For example, we could consider a subset of this points which typically represents different objects, right? And in order to do this mapping and localization stuff, we could first of all extract some features from these objects. For example, the shape, the size. So anything related to this geometry of these objects, which allows you to find the correspondence corresponding between, right, the knowledge you got previously and your current observation, right? And for object detection and tracking prediction, some other data processing methods might be needed. For example, either based on pipeline, right, or end-to-end. So pipeline, according to the name, is a method built with different modules, different components. So we process the data like step by step, module by module. For example, in order to track an object, to check a person, we first of all segment the point cloud into different pieces, or sometimes we say it into different clusters. And then, based on some features, for example, geometry or any other features, we could identify, we could detect these objects. Say this is a human, this is a chair, this is a desk, this is a car. And then by some algorithms, for example, data association, carbon filter, whatever, then we could associate right, different examples across a sequence of data of scan. Then for this object tracking stuff. So end to end, I think the very popular method to realize this end to end method is this deep learning stuff, right? Say the input is a set of points, and we don't care. We don't have this different components and modules. We have only neural networks, which can be considered as a black box, right? And we just want the output. For example, which point belongs to a human, which point belongs to a chair or a car, right? So one of the fundamental problems, as I just mentioned, is the segmentation of the set of points. So for 2D, for sensory data generated by 2D LiDAR. So I think I have to speed up a little bit. There's no other name, no other than no set point. But for 3D LiDAR, we have this new name, which is called point cloud. So the segmentation of point cloud can be something we have to pay attention. So what we did previously for this problem is we compared 5 state-of-the-art and somehow benchmark these 5 methods, and found out that for one of these data sets, which is generated, which is made with 16-layer LiDAR, this adaptive clustering is the best. So the reason I mentioned this, because this is my method. And then there's different ranking for the other 2 data sets. The second one is made by jointly made by by myself and the professor and Koenig, with 22 layers 3D LiDAR. Then the third one is just retrieved from KT with 64 layers LiDAR. So if you are interested, here is the QR code. I don't know if I should share the slide afterwards, but it's quite easy to find out this LiDAR benchmark LIPC. But with LiDAR, we have typically some limitations, especially under this adverse weather conditions. I think this is also one of the reasons I'm here. So LiDAR is not really working very well on the foggy, raining, and snowing days. Because according to the principle of this reflection, right, echo stuff, you could imagine that laser beam, when the laser beam reached the droplet, for example, reach the water droplets, it actually can be reflected by these water droplets. But actually, no, this is not a part of the object. For example, the road participants, like a pedestrian, cars, cyclist, right? So all these false echoes are considered as noises. So obviously, one of the very iterative ideas is to remove these noises, right? But how? Because there's typically two kind of methods to deal with these problems. One is bottom up. Say we first of all build the physical model, right, of this phenomenon, this noise, then try to somehow remove it. Then the other is up-down method. Sometimes could be data driver method, right? So from according to our experience, bottom up is not that efficient. It's not that easy to really remove these noises. While data driven can be actually alternative. But collecting this data on the foggy, running, noisy, snowing day, I mean, it's really tricky. It's really tricky. So what we did is to build an artificial chamber in France and try to install some pipes to generate this fog, no rain, with a well control system. Say we could really control the volume of this different adverse weathers. Then we collect data. We just put a 3D LiDAR, for example, very down here, and some objects inside of the chamber, and try to modify the volumes of fog, of rain, and collect data. So thanks to the data collected, we could somehow model these different phenomena by data-driven methods, right? Deep learning or not. So I wouldn't go into the methods, but only show you the results. So these are the real data we collected in the chamber, and these are the simulated data with the here and here. We actually used, we obtained with the model we learned from the real data. So as you can see, it's not exactly the same, but I mean, for autonomous driving, it's fair enough to understand, the visibility, especially the visibility on the different weather conditions, which is quite important, right? Because we know where are the other road participants in order to correctly and safely react to them. So here are actually legs of Philippe, right? And if you can recognize the ground is just over there. So Philippe built this fantastic system to record some data with a radar here, right? So the project was to understand on the foggy or smoky environments, because we know the LiDAR won't work. So what we could do if we want to detect people, right, is quite essential for search and rescue tasks. Then we could use radar. So Philippe collected some data, and also by using data-driven method, he built a model to detect these humans around it. So regarding the second part, robot learning. So at the UTBM, we care about this, how to learn a model, of the environment, in a short time, fast. While instead, at the CTU here, the chronorobotics lab, people focus more on this lifelong learning. So there's overlapping between these two topics, and we are trying to find out what are the links between these two. But in order to understand what is the research topic at the UTBM, which is online learning, here I put 3 learning schemes in order to better understand the differences. So offline learning is quite popular method. Say you collect data, you annotate or not those data, but for sure you need human intervention to build this model based on the data collected, right? And once you deployed your model into any kind of systems, you don't have the rights, or say the model cannot be modified anymore. While the second way scheme is incremental learning, which is not really necessary human intervention to build this model, but it can be, of course. And especially, this learning scheme can deal with this, data stream, say, data coming over time. While online learning really want to remove completely this human intervention and really leave the model to learn by its own, by itself. So one of the recent work done at the UTBM is this online learning for autonomous driving, especially for this road participant detection, which is done by one of my PhD students, Hui. So he's just over there. If you want to learn more, he's the guy and the right guy to share with you. So the overall idea is just to reuse one sensor to train another, simply said. But the real motivation behind is that we found out that it's really tricky to learn to train a model with 3D LiDAR, because there are just a few points, a set of sparse points. It's not easy to annotate. It's not easy to find the features. So we found out that. So we asked them ourselves, why not to use the really cool results from deep learning, especially, and the community for this camera-based object detection. Then transfer transfer somehow the capability from camera to LiDAR. So that's how he built this the fantastic scheme, learning scheme, say to use off-the-shelf camera-based detector to train the 3D LiDAR-based detector. So this is just an implementation. As you can see here, neural network is used for off-the-shelf camera-based detector. Then traditional, learning methods typically is this random forest is used for 3D LiDAR-based detector. The reason we choose this traditional method for 3D detector is we want to really to have our results applicable, applicable, sorry, for industry players, right? Autonomous driving essentially is a topic, closely linked, academia and the industry. So he actually got a really cool results, which can be pulled by this KITTI dataset ranking, which is one of the most popular datasets in this autonomous driving community. So he got 91 and 125 respectively for pedestrian and bicycle cyclist detection in 3D, while 22, 22nd and 16th place for pedestrian and cyclist in 2D. So I have to say this is awesome results because the model learned completely in an autonomous way without any human intervention. I wouldn't say other methods are based on human intervention, but for sure ours is in this way. And also pedestrian, according to the community, pedestrian cyclists are much more challenged to detect compared to cars, because cars are relatively easier and larger and easier to detect. And as you can see here, the differences between ours and other methods is not really huge. As you can see, 0.0 or 0.12% differences. So the last part is about software hardware integration we have done at the UTBM. Again, still with 3D LiDAR, we want to look into deeper into this usage, or say integration, especially onto mobile platforms. So here is an example to show you integration scheme. So still on top of the robots, like a tower, in order to have a panoramic view, but also with this 0.8 centimeters higher, we could detect pedestrians with a reasonable distance. So the settings, what I would like to say, are carefully selected and measured. So in order to better compare with the state-of-the-art and other methods, we were trying to build a new benchmark scheme. So we define some places for the robots and for the human, and we clearly specify the distance, the moving distance, and the moving distance between different places, which we call the waypoints, and then with some matrix, especially from two parts, objective part, subjective part, right? To merge this, social acceptance of this, 3D LiDAR-based robots. So what we are looking for now is to find the link between the subjective matrix and objective matrix. If one can prove another, that would be awesome, because today it's really hard to convince people with different background to say, okay, with this objective method, objective matrix, this method is better than the other, right? Or with subjective matrix, probably is another result. So we try to find the links between these two matrix. And so here is a video to show you our latest results with this Toyota robots. For the research topic behind this faster decision making. In this context, we want to have our robots to pick up the right object over time. So let me speed up a little bit the video. So for example here, as you can see, the robot chose to pick up, first of all, the ball. The algorithm behind is quite simple. The robots pick up always the closest object. Right. So okay. So due to limited time, let me just wrap up today's talk. We introduced some recent applications of 3D LiDAR in field of mobile robotics, including autonomous driving, and some methods of processing LiDAR data, and also some limitations of this kind of device, especially under adverse weather conditions. Then we discussed how mobile robots can achieve learning, long-term autonomy through learning. Then we ended up with some insights on this hardware software integration and faster decision making for mobile robots. So that's it. I spent a little bit more time than expected. I'm sorry. So if you have any questions, so please just ask. Yeah, for sure. The first problem is the size.
But then, is it like a physical limitation that we cannot make it smaller, or is it just a technological problem that we could see smaller 3D LiDARs with lower grade parameters in the
I would choose the second one. I think it's just about technical, no problem. We will, I think we will definitely see smaller LiDAR in the future, and then we could integrate into small platform.
Also, what I see as a basic limitation, like compared to the LiDARs to the cameras, is that like you always have a mechanical component in the LiDAR, right?
Yeah.
So is there any, do you see any trends in these solid state LiDARs that are announced?
Yeah.
Or do you see the solid state LiDAR as a, fusion energy that is 10 years later?
The example, the scheme, the principal scheme I gave here is for the mechanical LiDAR. So you always have this spanning mechanism inside. To be honest, it's harder to reduce the size of these mechanisms. But as you just mentioned, I would say MEMS can be, the solid LiDAR can be, or flash LiDAR can be smaller. Yeah.
Okay, I guess if there are no other questions, then we can conclude the seminar. Thank you again, Zhi.
Okay, thank you.